Assalamualaikum and hi, we are from Group 11. Topic that we are going to present is the influence of cache size. Before that, let me introduce you to our team members. Our team consists of 4 people, which are Alia Mawadah as our team leader, Muhammad Murshid, Ahmad Solihuddin, and me, Siti Hadijah. Okay, so first of all, cache is a critical component in computer architecture. Cache memory improves system performance by reducing average access time between CPU and main memory. This project used the SMP cache simulator to analyze the impact of cache size on cache miss rate. Simulator allows observation of real workload behavior, not just theoretical analysis. Our group has been assigned with Project 2, Set A, COMP Benchmark Trace. COMP is an integer-based compression program that uses Lamper-Ziv compression technique, suitable for analyzing cache locality and misbehavior. Our main objective is to observe how different cache size affect misread. For the design pattern provides structured and reusable problem-solving approach. It helps learners to avoid trial and error methods and apply systematic reasoning. In this project, we applied a problem solution mapping framework. There are 5 solution steps. First, identify fixed architectural parameters, vary cache size, run simulation using SMP cache, record results, and compare performance trends. The benefit of the design pattern is it helps focus on key relationships between cache configuration and program behavior. Last but not least, cognitive theory. Cognitive theory explains how learners process and organize information. This helps reduce cognitive overload for beginners. Beginners may face cognitive overload due to many abstract concepts or multiple design pattern choices. It also guides us to focus on system goals and key relationships, and supports better design pattern selection and decision making.
I will explain for the simulation task. We use the SMPCAD simulator. The benchmark used is COMP from Project 2 Set A. The main purpose of this simulation is to see how cache size affect cache miss rate. We use a step-by-step approach where only cache size is changed and all other system settings are kept the same. This helps us do the simulation in a controlled and fair way. The problem is that cache size greatly affect cache performance. If the cache size is small, the miss rate will be high. When the miss rate is high, the system need to access memory more often, which makes the system slower. So the simulation is done to study the effect of different cache size and to find the point where increasing cache size no longer improve performance much. And the objective of the simulation are first to study the relationship between cache size and miss rate. Second, to observe the miss rate trend as cache size increase. And third, to see whether a larger cache really improve performance for the COMP workload. Okay, next, this slide show the system configuration used in the simulation. The simulation is run using one processor only to maintain a controlled environment. The cache coherence protocol used is MESI, and the bus arbitration scheme is random. The word size is 16-bit with 16 words per block, resulting in a block size of 32 byte. The main memory contains 2,192 blocks, which is equivalent to 256 kilobyte, while the cache contains 128 blocks, giving a cache size of 4 kilobyte. The cache use fully associative mapping with the LRU replacement policy. This configuration is chosen to eliminate conflict miss. So the analysis focus mainly on capacity miss caused by cache size variation. On the side, we can see the SMB cache simulation interface, which is used to set all these parameters. During the simulation, all the parameters are kept constant, and only the cache size is varied in different simulation run. From the result, we can see that the cache miss rate decrease when cache size increase. A larger cache can store more frequently user data and instruction, so it benefits from temporal locality and spatial locality. Because of this, capacity miss are reduced and conflict miss do not occur due to the fully associative cache. As cache size become larger, the miss rate start to stabilize. This happens when the cache is already big enough to store the working set of the COMP program. After that, increasing cache size gives only small performance improvement. which is known as diminishing return.
In trace file selection and environment for this experiment, we selected the COMP.PRG benchmark trace, which represents an integer-based compression workload commonly used in cached performance studies. The trace contains 2,524 memory accesses, including 2,055 instruction fetches, 113 data reads, and 356 data writes, with a total file size of 29 kilobytes. This simulation was run using a single processor configuration to maintain a controlled environment. This removed the effect of multiprocessor cache coherence and allowed us to focus purely on cache behavior. The COMP trace was chosen because it exhibits repetitive memory access patterns, making it suitable for analyzing cache hits, misses, and misread trends. Next is the simulation execution. The benchmark successfully completed all the 2,524 simulation steps, confirming correct and uninterrupted execution. The same trace was tested across different cache size configurations, allowing performance comparison under varying cache capacities. The complete status indicates that all instruction and data accesses were recorded accurately, ensuring reliable results for performance analysis. For performance evaluation, we focused on the cache miss rate. The results show a clear inverse relationship between cache size and miss rate. As cache size increased, the miss rate decreased. Smaller cache cannot hold the full working cell, causing frequent evasions and more main memory accesses. Larger caches retain more frequently used data and instructions, reducing memory latency and improving overall performance. And at the visualizing performance trends at the performance graph, we can see that at smaller cache size, there is a steep reduction in miss rate, showing significant performance improvement. As cache size continues to increase, the improvement becomes smaller, demonstrating the concept of diminishing returns. This helped identify an efficient and balanced cache size for the COMP.
We're explaining about miss rate table, answering the questions, and conclude this presentation. So based on the miss rate table, you can see that the miss rate decreases as the size of the cache increases. As for the question, does the miss rate increase or decrease as the cache size increases? Why? The miss rate decreases as the cache size increases because the larger the cache size, the more data and instruction can be stored, thus reducing the misses. Second question, does the increment or decrement happen for all the benchmarks, or does it depend on the different locality grades? All benchmarks show reduction in miss rate as the cache increases. The miss rate is affected by locality grade since larger cache size benefits from special locality. As for the question, what does it happen with the capacity and conflict misses when you enlarge the cache? When the cache is enlarged, the capacity will increase simultaneously decreasing the miss rate. Are there conflict misses in this experiment? Why? Yes, conflict misses occurs in this experiment. This occurs when no block of main memory tries to occupy an already filled lines. As for the question of the task, in this experiment, it may be observed that for great cache sizes, the miss rate is stabilized. Why? This is because there is less number of entries in the cache. Second, we can also see great differences of miss rate for a concrete increment of cache size. What do this great difference indicate? The great difference of miss rate indicates that the cache is stabilizing, thus the cause of the great differences. Third, do these great differences of miss rate appear at the same point for all the programs? Why? No, these great differences of miss rate does not appear at the same point because each program have different working sets and memory access pattern. As the question for the fourth task, does the increases of cache size improve the system performance? Yes, the increase of cache size will improve the system performance because it will reduce the memory access delay and allow faster instruction executions, therefore improving overall performance. As for the conclusion, the main focus of this assignment is to analyze the influence of cache sizes with miss rates using three different memory traces, which are CEXP, COMP, and EAR. After conducting the assignment using SMP cache, where configuration to caches was made, it showed that the cache size does influence the miss rates. This is proven by the data results that when the cache size increases, the miss rate for multiprocessor, cache, and memory block then decreases. In conclusion, cache size have an effect on miss rates, plus having low miss rates means improved system performance. Thank you.